our seminar today. So it's a pleasure for me to announce Engin Tola, our presenter. And Engin Tola received his BS and MS degrees in Electrical and Electronics Engineering from Middle East Technical University in 2003 and 2005 respectively. After that, he completed his PhD studies in computer vision from EPFL in 2010. He then founded Aurvis R&D. It's a computer vision and machine learning research and development company in Ankara. He's primarily interested in 3D geometrical scene understanding, reconstruction, localization, and exploration problems in real time. During his 10 years in the industry, he developed algorithms and products for companies like Autodesk, Drone, Diplo, and TÜBİTAK Space Research Center. He's also a co-founder of several companies, including a San Francisco-based AI-powered data extraction company. So.
Thank you. Welcome to my talk today. I'm Engin Tola. I have a company called Aurvis R&D. Today I will be talking about the star tracker algorithm that we have developed together with TÜBİTAK Space Research Center. And before going into that, I would like to show a few slides about the type of problems that we work in Aurvis. So we mainly work on computer vision and pattern recognition problems. We develop customized solutions for these problems. Our main interest is extracting geometrical information from images and videos. And so this is a slide showing our research in geometric and photometric calibration. For these problems, basically what you try to do is, given a bunch of images or video sequences, we are trying to calibrate each and every one of those frames. We calibrate, what I mean is you are trying to find the rotation, translation, extrinsic calibrations, plus the intrinsic calibrations. And this was actually my master's work with Dr. Aydın here, Professor Aydın here. So I started with this type of research in my career. After doing, so the geometric calibration, we are working on geometric calibration between images, but we also worked on problems like trying to calibrate RGB images with images of different modalities. Here you see a research result of trying to calibrate an RGB image with respect to the reflectance information you are getting from a LiDAR device. So the purpose was given, for example, you scan this room with a LiDAR and you have a camera, you move around, you grab some pictures, you want to texturize the LiDAR. To be able to do that, you need to be able to, you need to know where the images are taken from. So this application was targeting that kind of scenarios. Other types of geometric problems that we work on is computing 3D point cloud models from images. Once you calibrate images, once you know where the images are taken from, you compute depth maps for each of the images, and then you try to fuse them in a coherent way so that you end up with a consistent 3D model of a scene. These are objects for images taken from turning around, rotating around, ground-based observations. But we also work with drone data, and these are recent results that we produced about texturization and meshing of these point cloud models. So when you capture images with a drone, what you do is you capture images, you calibrate them, you do a georeferencing so that you know where they are taken from, and also you bump up to a metric resolution. Then after that, you compute a point cloud, you compute a mesh, and then you texturize it. So we work on a bunch of industrial scenes like this and some architectural scenes mostly. So we are having more and more industrial scenes which have thin structures, which is kind of driving our research right now. And beyond that, once you capture, extract a 3D model of a scene, what you do is you try to extract more information from that. This research was related with that. We were trying to extract the roof, automatically extract roof polygons from 3D models, metric, so that you can do some metric measurements on it. This was related with some company for extracting, for using these sort of outputs for solar cell placements, so that when you have this, you can automatically say this roof is going to get this many suns per year, so that you can have this many watts produced, something like that. And lastly, we are also working on real-time operation of these kind of technologies. This is for a small toy problem. This is called a visual inertial odometry, also simultaneous localization and mapping. What you are trying to do there is you have a video stream coming in, this one, and you are trying to build an environment model, and then you try to localize yourself in that environment. So, as I said, I mean, these are recent research results, and we are now trying to commercialize on that for flying autonomous platforms. And lastly, today's topic is related with the work we have been doing with TÜBİTAK Space Research Center. As I said, this device is being developed by TÜBİTAK, and I am consulting there, and we are developing the algorithm for the device. I'm going to go into more details about that. So let's first start to define what a star tracker is. A star tracker is an electro-optical celestial referencing device that is used to orient the spacecraft's location, orientation. So this is kind of a fancy way of saying, okay, you have a camera on a satellite, and what you are trying to do is, this camera is looking towards the stars, and you are trying to find the orientation of your satellite with that information. So our inputs are a bunch of black images where you have some spots on it, and those spots are stars. So here you can see a number of different star trackers. The one on top is from Solan Z26 star tracker. It's a small one. It's about this big. It has an optical hat and an electronic unit. Optical hat is used to capture the images, and an electronic unit contains the algorithms that does the orientation estimation. And the one on the bottom, which looks much more cooler than that, is ball area spaces high accuracy star tracker. So it's, I think, about 2 meters in length, and these dimensions are sort of a byproduct of the requirements of the star tracker. So for high accuracy star trackers, you kind of need better optics, and that means that bigger lenses, and when you have to use bigger lenses, the weight and the volume requirements of the device increases. So to give some info about that, star trackers are used in all satellites in orbit today. It's the most accurate orientation device that you have on a satellite, and there are usually more than one star tracker on each satellite, because if one gets broken, you want to have a backup about that. But also there's now more star trackers with multiple optical heads. This is due to the fact that with a single optical head, the problem geometry sort of enforces the results in an accuracy where the z direction accuracy is sort of about 5 times better than the error around that direction. So if you want to have 3 axis accuracy levels, each uniform and each really good, you want to have multiple optical heads, and we are now seeing more star trackers like that. And some requirements about the star trackers: you want them to be real time, better because if you want to move your satellites in a high-speed environment, like for example, when you have Earth-observing satellites, you kind of need to be able to move them in a speedy fashion. So higher the star tracker's operating output is better for controlling the satellite. So as I said, the accuracy requirement changes from mission to mission. For geocentric, for Earth observing satellites, you want them, you don't need that high accuracy, but if you want to have a telescope which observes space, for example, the Hubble telescope in really far away places, you need to have really high accuracy star trackers. And for example, this sort of devices can come into play. And what are other things? Yeah, you are in space, so it needs to be robust to temperature changes. This looks like a mechanical issue, but also affects electronics and optics too, because with the temperature changes, the device sort of moves around a bit. So the optical centers and the focal length changes with the temperature changes, so your algorithm needs to be robust against that. Again, you have vibrations during launch, so things tend to move around, so you again need to be robust against that sort of stuff. Also, you are undergoing a lot of radiation. So radiation has two things that's kind of problematic. First of all, it darkens the lenses, so the light that you are seeing from the stars gets diminished as it is being used. That's one problem. The second is the electronical in your sensors. When a high energy particle hits your sensor, they generate images sort of like a star. So you end up having false stars in your image plane. So the algorithm also needs to be robust against that sort of stuff. So a star tracker has two operation modes, two main operation modes. We have a bunch more, but these are the most important ones. The first one is the lost in space mode, where you start the star tracker, you don't know anything, an image comes and you are trying to identify your orientation and the stars that you are seeing in there. So this is also called attribute acquisition mode, and it's, as I said, the star tracker is called started and tries to initialize itself. It recognizes star patterns and identifies stars. It's sort of like what sailors did years ago when they are sailing. So at night, when you look at the stars, you see clusters of stars, you recognize them, you know where they are in terms of orientation-wise, east, west, north. So depending, with respect to that, you orient yourself. So we are doing something similar. We kind of combine stars together in our image sensors to generate some kind of signatures, and then from that we try to recognize a new image based on that. And so the lost in space mode estimates its orientation. Also, it also needs to estimate the relative speed, angular rate of the spacecraft, because it needs to go into the tracking mode. So to be able to do that, you need to kind of meet the speed of the satellite as well. It initializes the optics calibration, as I said, depending on temperature and launch. You can have things moving around. These movements are about like 50-60 microns, but if you don't compensate for them, they have an effect on your output accuracy. So you need to be able to calibrate for those two. Then it switches the mode to the tracking mode. This is our initialization mode. So this doesn't need to be real time. You can have about a few seconds to do that. But the tracking mode, you need it to be real time. So what you want is, what is ideal is, you launch a satellite, you start your star tracker, it captures an image, initializes itself, goes to tracking mode, and stays there for 15 years. That's the ideal scenario, but it never happens. Of course, you switch back to the identification mode a few times. But as I said, all the optimizations, all the calibration stuff is kind of more important in the tracking mode. In the tracking mode, what we do is, okay, you have initialize yourself, you have a position and you know the identities of the stars in your field of view. In the next frame, another frame comes and you try to update your orientation and angular rates based on that. So how do we do that? We use tracking, we use Kalman filters. I'm going to go into the details about that. You track the star positions. As you move around, some stars go outside the field of view and some new ones come in. You decide which stars to follow, which stars to track. And we really don't have a lot of computational power there, so we kind of have to pick which stars are much more informative, much more accurate, and we need to go following them. And yeah, another thing is, again, in every loop we also update our intrinsics because of the temperature problems. So before going into the details of those two modes, I want to first talk about the design decisions that you have to make while building your hardware so that you can achieve the accuracy and speed requirements of the tracking and attribute acquisition modes. So as I said, we are observing stars, so our device needs to see these stars. And there are billions of stars, but the optics only allows us to see a certain number of them. And for example, human eye can see about 6,500 stars in a clear night with no light pollution. But our star trackers are kind of seeing only about 3,000 of them. And they are not uniformly distributed in the celestial sphere, so in some places you have lots of stars, in some places you have a few, and their brightnesses changes. So the requirement is that wherever I look at, I should be able to orient myself. So this means that you kind of have a limiting magnitude of a star that you can see, and that kind of determines your overall hardware specification. So how do we decide that? By computing the signal-to-noise ratio of a given star. So from astronomical catalogs, we can find out a lot of information about stars. The two things are most important for us. Okay, three things. First, their location and their sort of how accurate is this information. The second thing is if they are moving fast or not. Stars are not constant, they move around. So you want to orient yourself to using more stationary stars. And the third thing is their temperature. So because we have this nice blackbody formulation that gives us information about how many photons a star emits based on at which wavelength based on their temperature. So I'm not going to go into too many details about that, but it's this blackbody formulation gives us, this is the wavelength, and based on the temperature, we see that, for example, this is for sun. It gives us an information about how many photons are emitted per wavelength. And this is, by the way, the blue one is the actual measurement, and the yellow one is the estimate according to this blackbody radiation formulation. So by using this formulation, which starts by just using the temperature of the star, we try to, we basically link this information to the brightness information that we have from star catalogs. And okay, so for an SNR, we are trying to estimate how many electrons are generated from a star. And for that estimation, we have this kind of a nice compact formula which depends on all those parameters, which we are not going to talk about, don't worry. So actual thing is we kind of want to have this equation which relates the star's apparent magnitude, which is available in star catalogs, and its temperature. So once we have that, we kind of are able to then estimate how many electrons that this star can generate. By the way, this formulation, okay, the bottom of the presentation is not here, so there's a paper link there where you can look at that, but it's not on the screen. If you're interested, just let me know. Anyway, so for this, using this formulation, we can estimate how many electrons a star is going to generate on our sensor, given the properties of the optical chain we have, like its quantum efficiency, which tells us how many, which tells us the ratio of photon to electron conversions for a given wavelength. Also, its fill factor, the amount of the ratio of photosensitive area on the pixels, the optical aperture, and the transitivity of the aperture. So once we have these values determined from our design, then we can estimate the SNR of the system. And so the noises coming from the electronical sources are also given here, which is in the SNR noise terms here. So we have the readout noise, which is the electronic noise but of the sensor, which means that which tells us the amount of noise that you encounter whenever you digitize an image. It doesn't need to have any. Sorry about that. So readout noise is the noise that you have from the electronics about A to D conversions, pixel geometry, that sort of stuff. The second noise term we have is due to thermal noise. So any pixel generates electrons at a given temperature. So we want to discriminate this from the electrons generated from the actual light source. So this is therefore an plus. And also you have another term which generates more electrons in the sensor due to backlight scattering. So if, depending on your location in the atmosphere, you can have some background illumination, and that illumination also causes you have to have some electrons generated in the sensor. So once you have this SNR formulation, what we do is we kind of draw some curves depending on the different characteristics of our electrical and optical equipment that we use. For example, for this green curve, what we have is a 15 micron pixel, 15 by 15, and the F number of this optical device is 1.6, I think, and with some other parameters like the quantum efficiency, fill factor, the exposure times, and whatever. So you have this nice curve, which tells you, and by the way, the x direction is the star's apparent magnitude. So this curve tells you which stars you are able to detect. So when you are picking your different electrical and optical design parameters, you look at these SNR curves and you say, okay, if I want my SNR to be at least 4, then I can see up to visible magnitude 6.3. And then you go back to your catalog, star catalog, and you say that, okay, I can see only these stars. Then you look at their distribution and you say, okay, this is enough for my field of view, if it's enough or not. And during the design of the star tracker, you make use of these curves here. So once you have designed your hardware, let's talk about some things about the algorithms that you use to detect this pattern determination problem. So what we are trying to do, as I said, is given the images of stars, we are trying to identify these stars so that we can find our orientation. So it has 3 stages. You first, given an image, you first do centroiding. You detect which locations are stars. And then you try to identify them, And once you identify them, you do kind of a small optimization problem, and you solve the orientation matrix you are after. So to be able to do that, what we do is we first index our star catalog. What does this mean is, as I said, we have about 3,000 stars, and we want to be able to recognize a given image, any pattern in a given image these stars can produce. So what we do is we kind of generate images that mimic what we will see in real use cases, given the field of views and the parameters of the sensors that they are going to use. And from these images, we compute geometric hashes for these grouping of stars. So here, for example, what we show is we kind of get some number of stars here. We use only 4 grouping stars. And from these 4 stars, we try to compute a geometric hash so that at runtime we can recognize this constellation and then identify these stars. So we do this operation for all the celestial sphere because the star tracker can look in any direction and generate these indices. I'm going to explain what we use for these hashes, but when we are doing this indexing, this tessellation, we have some number of parameters that we need to be aware of. First of all, any given 4 spots shouldn't be used as a hash, because as a grouping, because they can have some e-post configuration which will mimic other configurations in other parts of the sky. So you need to get rid of some duplicate hashes. Also, another thing is that there might be some uncertainties about their hashes, so you also get rid of those. But during indexing, you kind of try to generate all the possible combinations of stars that you might encounter in your field of view. Once you have that, at runtime you just try to find which which index that you are matching to. So I talked about the hash, geometric hash that we use to compute these signatures. It's explained here. What we are doing is, given any 4 points in an image plane, we want to have a mapping of these so that they have a unique signature that we can match against. So this is what we do. Given any 4 points, we transform them with their scale, rotation, and translation. We apply these transformations so that one of the spots goes to in a near coordinate frame to 0, 0, and the other goes to 1, 1. And your geometric hash is just the x and y coordinates of these remaining 2 stars. This is a mapping which is unique if you ensure that XC and XT are inside this unit circle and XC is less than XT. So if you think about that, what we are trying to do is we try to identify these 4 points that we encounter in images. So to be able to do that, we need to have some kind of unique mapping from any configuration that we can see them on the image plane to a more easily matchable space. So we do this transformation so that we can achieve this. There are a few points here. So these signatures are so when you match a given signature to the index signature, what happens is you basically say that, okay, in my image, this spot corresponds to A, this spot corresponds to B, this is C, this is D. And these A, B, C, D then tell you which ID, which star that you have seen in your catalog. So from the image space, XY coordinates, then you are able to identify which stars that you are seeing in your catalog. when you have that, then you can compute a transformation that for your missing rotation information. So, as I said, if we identify those 4 points, I know their directions from my star catalog, and this Qi represents the direction vector in inertial reference frame corresponding to the star, and this Pi is the direction vector that I'm computing from the xy coordinates inside the image by using the intrinsic parameters of the camera, the focal length and the principal point. So this assumes a simple transformation here. We are using a perspective camera model here. So the cost function is basically representing the transformation of 4 direction vectors to another 4 direction vectors. And what we are trying to solve is the rotation matrix. And solution is found by this equation here. You are applying a similar way decomposition to the transform problem onto the B matrix. This is kind of a famous equation. It's called a Bach-Pass problem. It's used for rotation estimation in many different scenarios. Okay, let's sum up in this slide a bit. So when you are running in, when you have a new frame, what happens is you get a bunch of spots. So this is a simulated output. The green spots represent real stars. The red ones are the spots that occur due to radiation. So there are a bunch of different combinations that you can have to compute these quads. And what we try to do is, given a quad like this, we first try to identify it by matching its hash to the indexed hash values that we compute from our catalog. If we can find a match, then it means that I have identified these 4 stars, and using this equations here, then I can find my orientation. Once I found the orientation, once I find where I am looking at in space, then it means that, but I also know which stars should be visible in that viewpoint. So what I do is I project all the stars to the image frame and try to find matching spots that correspond to the stars in my catalog. For example, I project the stars in this frame and I count how many matching spots that I can find on this image plane. So this gives me a kind of a validation, number of matching spots give me if the found rotation matrix is true or not. It gives me a score. And if there's enough validations, then I say that, okay, I found the orientation of this frame. Once I do that, then I try to switch to the tracking mode, because we have already found the identification of that frame, rotation axis of that frame. So before going into that, let's look at some of the artifacts that we can have in processing images. So the first row is an ideal point spread function for a point light source. And this is kind of a sombrero looking like of signature here. I don't know if you are seeing this or not, but its profile is here. So we never have this kind of signature. What we have more often looks like these kind of signatures because we have lots of distortions. First of all, point spread functions changes with respect to the wavelength of the light that you are seeing, and since stars emit different different composition of wavelengths, you end up with different point spread functions for each star. So you don't always have a nice Gaussian looking shape. The second thing is we have distortions on the image plane due to optical problems. And especially, for example, this PSF is in the center of the image, but as you go towards the edges of the image sensor, you tend to have spots looking more and more like this, so they are losing their symmetry due to the imperfections in your optical chain. And we have other sources of noise, like electronic sensor noise. Some pixels, however much light you shine on them, do not generate any electrons, so they are dark pixels. There are also some other pixels that you have due to temperature, they keep generating lots of electrons. They are defective, so you have hot pixels as well. So if any of your stars fall onto that kind of problematic points, you end up extracting their coordinates wrongly, and then this affects your attitude errors, accuracies. So you kind of want to keep an eye on your sensor, because this degrades with the radiation that you are encountering. And here you can see some of the effects of radiation. You tend to have, when you apply radiation to an electronic sensor, you kind of have streaks and spots occurring in your image sensor. These could be mistaken with actual images of stars. Your algorithm kind of needs to be robust against these things. And one other thing is you still have distortions due to optics. And also, your image plane and your optical light wavefronts should ideally be perpendicular to each other, but it's not always so. So there can be some inclination between the two planes. And when that happens, you instead of having a nice linear perspective model, you tend to have distortions in your images. For example, when you also have the radial distortion problem, where straight lines becomes banded. I think that you have seen that before in your images. For example, what happens is instead of falling to a correct location, they go and fall in like due to distortion and artifacts about your inclination problems. They can fall into other places. So you need to compensate for that sort of thing. You need to calibrate your sensors to measure these distortions. So during our online operation, we do not compensate for declination problems. We solve it only once after the identification phase, because they don't change much with the temperature changes, so we are not tracking them. But for the focal length and principal points, we compensate for them. Now I will talk a bit about the tracking algorithms that we are using. So it's composed of 3 different stages. You want to keep tracking the stars, which stars are the stars that you have identified before. We do attitude tracking, and also we do calibration tracking. A bit of detail about these 2 stages. We use a nested architecture here. The attitude tracking is using an indirect extended Kalman filter. We represent the orientation in terms of quaternions, but instead of using the quaternion, full 4-vector quaternion, we are using the quaternion update vector as our state vector. This way it becomes an indirect Kalman filter. I don't know if you're familiar with it or not. And we also assume a constant motion model. So because satellites don't tend to move a lot, so once they kind of spend most of their time under constant motion. So we optimize our algorithm with respect to that. And as I said, we don't have too much computational power, so we track at most 16 stars. That's the upper limit that our hardware can withstand. So there's also this problem. We want to keep everything deterministic computation time, so there are limits on the number of computations that you can do. So what happens is your observations are stars UV coordinates on your image plane. These are your measurements. And using these measurements, you track your attitude using the extended Kalman filter. Once you have an attitude output, in the next stage, we also update the calibration information. What we do is, again using the UV coordinates and the estimated quaternion output, we solve the calibration parameters, and we use the solved parameters as input to our calibration filter, another linear Kalman filter that we use for this purpose. And in the next updates, we basically use the updated focal length and principal points in our attitude propagation. So just a small slide to show how we compute the intrinsics. The equation is the same. We are still minimizing the difference between the estimated direction vector and the star catalog direction vectors. But this time we know the altitude from this. The input to this is the known solved altitude information. We also know the stars direction vectors. What we don't know, what we are trying to solve is the focal length and the principal point in this equation. So when you solve this, get the Jacobian and minimize it, you try to minimize it, turns into an AX equals B type of linear problem, and you solve it. After you solve it, as I said, you feed it to the calibration tracking algorithm. So just a few simulation results about this. So this shows the case where we try to track the altitude without having the calibration tracking. So this purple line is the actual focal length. This is somewhat exaggerated. It doesn't change this much, but we wanted to test our algorithm against that. So the designed focal length is here, 72 millimeters. And we try to track the altitude with this, and these are the error vectors, error values that you are getting from the by not updating the focal length, by not tracking. But if you also enable your calibration tracking, errors are much better. So kind of a detail about these two error values here. We are measuring coordinate frame to coordinate frame error metrics. So the error degree of freedom between two coordinate frames is only 2. So first one is you are trying to align your z direction. Once you align your z directions in two coordinate frames, the remaining degree of freedom goes to the rotation around that. So this is the error for aligning your bore sides, the z direction. And this is the error around that direction. As I said, using a single optical hat, you tend to have this kind of different error values for that. The z direction error is about 5 to 6 times better than the bore side error. This is due to the nature of the problem that we're trying to solve. So, okay, before that, okay, I think the slides are different in different locations, but okay, this is a simulation output that we have done. This is for identification. At every frame, we are trying to identify the stars and solve the rotation here. So this is kind of an orbit, simulated orbit. These are all the stars that you see. This simulation uses more stars than we are using, about I think 6,000 or 7,000. And this, let's stop this a bit. Okay, this 4-star quad is the one that we use to identify that frame, and once it is identified, the others are used to validate it, as I said. And this is the altitude errors in bore side and cross bore sides that you can see. So sorry about that, but this is only for identification. I don't have a simulation output for the tracking results. So just a couple more slides about using single versus multiple hats. This slide is showing the angular rate estimation that we are doing based on this quaternion. So these are the rotation vectors around x, y, and z axes. As you can see, the error around z, and this is, by the way, its distribution with respect to the amount of noise it has. So it's maybe much more clear here. X and y errors are smaller. The z error, rotation around z error. But if you use multiple hats, this is, for example, again, a single hat, and these results are for using two optical hats. So if you use, of course, they are not looking at the same direction. You need to have some kind of angle between them. The ideal is using 90 degrees, but it's not always possible to use a 90-degree optical hats due to the placement requirements on the satellite. 60 degree also works quite nicely, so we are simulating 60 degrees here. So yeah, I think this is the end of my presentation. Thanks for listening, and if you have any questions, I can try to answer them. Sorry about that, I just prepared it in the last 2 days, so it's a bit rushed, so I don't have too many details here. But yeah, any questions?